Right, the next question is about longitudinal waves, or not the next question, the next slide. And this shows a slinky spring here, and it's hard to see, but there are places here where the springs are a little bit closer together and here where they're wider apart. So you have compressions and rarefactions. So what type of energy is a wave transferring? Again, movement energy, so it's kinetic. What direction is energy moving in? So if the person who started the wave started at this end on the left, and this is where it ends up, then it's moving from left to right in that direction. In which direction is each part of the spring moving? Now each part of the spring is moving left to right as well. And so if I just draw that as an arrow down here in red and put an arrow on each end, because the spring's moving to and fro about its position and vibrating, you can see those two lines are parallel to each other. And so the springs are moving parallel to the direction that the energy is moving in. So we're going to write that down now in the definition. Definition of a longitudinal wave: the particles move parallel to the direction the wave is travelling in. And again, instead of saying the wave, you could say the direction the energy is travelling in. And so you can see there's your two lines, and left to right. Your particles are moving left to right, and your energy is moving from left over to right. When you speak to someone, so that's sound, and sound is our main example of a longitudinal wave. The air vibrates as a longitudinal wave. So you can see here that you have compressions, where the air particles are closer together and the pressure in there is higher. And then in between they are spread out a bit, and that's a rarefaction, where the air is spread out a little bit there. And so you can see another compression here. And eventually that will make your eardrum vibrate in here, and that will cause a sound wave. Okay, now this is very difficult to see. I appreciate you can't see the line at all there. So I'll just draw this out here. In this position here, you've got a compression, and then you've got waves spread out, and then you've another compression here, and then the waves are spread out, and so on. If you do have to draw this, really exaggerate the compression part and minimise the rarefaction part, so anybody looking at that can see. Now what that arrow represents there is, if you remember, a wavelength is the distance between points in successive waves which are in phase with each other. And so the middle of a compression to the middle of a compression there, you have got particles which are doing exactly the same thing. So that actually represents a wavelength between one compression and the next. Or you go from the middle of a rarefaction to the next, and that would also give you a wavelength. Now, transverse are longitudinal. So our longitudinal ones we always know are the ones which are to do with sound. So sound is a longitudinal wave, and that's that one. And then ultrasound is longitudinal, and that's that one there. So in here we have light, water waves, ultraviolet. Now there's two more here, and these are earthquake waves. I wouldn't really maybe advise that you would learn those in case you get mixed up, but there are two types of earthquake waves, and they travel in different ways from the source of an earthquake. One of them is an S wave and the other is a P wave. The S wave, if you turn S on its side, it's like that there. And so S on its side is a transverse wave. So that's how you remember the S waves for earthquake waves are transverse waves, and then the other type of earthquake waves, P waves, are longitudinal. And that's really the only other type of longitudinal wave that you have. I mean, the ultrasound is sound, so P waves are the only other type of longitudinal wave that we would actually give an example of. Right, now we've defined all these things to do with waves, including wavelength and frequency, and we can determine the speed that a wave travels at if we know the wavelength and the frequency. And it's given by the wave equation, and the wave equation is that speed, which is denoted by a V, is equal to frequency multiplied by wavelength. The units are frequencies measured in hertz, wavelength is measured in meters, and speed then is measured in meters per second. Now an alternative unit for wavelength could be centimeters, and if that was the case then your speed would be measured in centimeters per second. So just be aware of that. But if you do need an answer in meters per second, you must have your wavelength in meters as opposed to centimeters. Okay, so now we've got a question here, or a table to fill in. What are waves? First of all, they have a frequency of 2 Hz and a wavelength of 1.5 meters. So if I just write the equation, V is equal to lambda f at the top, you're multiplying lambda by f, 1.5 by 2 gives you 3 for your first answer there. Mexican wave, which is people moving up and down, wavelength of 40 meters and a speed of 8. So if we just rearrange your equation, we're looking for frequency. So frequency is V over lambda, and V is 8, and lambda is 40. So 8 goes into 45 times, so it's 1/5 or 0.2 Hertz is your frequency. The next one there is a musical note. It's a frequency of 256 Hertz and a speed of 339. So again, if we rearrange this, we're looking for lambda. So lambda is equal to V over F. And so that's going to be equal to 339 divided by 256. So it's 339 divided by 256. That gives you 1.32 meters. 1.32. The next one is a rope. And again, we're just finding V equals lambda f. So it's 3 multiplied by 0.8. And that gives you 2.4 meters per second. And then the last one is ultrasound. It's got a huge frequency, 35,000 Hertz, and a speed of 339. So again, we're looking for lambda. Just push that up a wee bit so you see it. So lambda is equal to V over F. And so that's 339 divided by 35,000. And that gives you a very small number, 0.0096 or 97. So it's a very, very small wavelength this time for ultrasound. And you know that ultrasound waves are waves of a very, very high frequency, and therefore they must have a very tiny wavelength if that's the case. Okay, so this is a little wave question. If you can see that there, the diagram shows ripples in a pond, and it shows you the wavelength between them, and the wavelength is from one ripple to the top of one ripple to the top of the next, or really from the top of a set of crests to the top of a next. Is this an example of a transverse or longitudinal wave? So obviously it's in water, so it must be transverse. If the wavelength of the waves is 0.15 meters and the frequency is 0.2 Hertz, calculate the speed of the wave. So you're using V equals lambda f, and that is equal to 0.15 multiplied by 0.2. And so 0.15 by 0.2 gives you 0.03 meters per second. So we know it's meters per second because the wavelength has been measured in meters.